Hello, and welcome to our presentation, People Ruin Everything, How the Presence of Humans Can Change Prey Behavior. We are Team 1053. I'm Nicole, joined with Regan and Spud. So the situation is that in the presence of non-predatory humans, prey animals become desensitized to other predators. So as college students, we often interact with the squirrels on campus, and we wonder, how is this affecting the squirrel's predator sensitivity? The given questions that we're looking to answer are: what happens when a group of people enters a new area? So animals that interact with each other are exposed to human activity, and thinking about the impact of those behavioral changes over time. And what happens when humans move out of said systems? The humans abandon the area. Is the damage already done, and can the ecosystem be restored? So in the context of our question, we'll see that people enter the college campus as school starts and leave campus as school ends in the summer. Here's a quick outline of where we'll take you on this presentation, starting with the predator-prey model and the SIR model, then going into some of the assumptions and initial conditions that we had to set, and adapting those two models to fit our situation, going over the results, and then some future possibilities.
Then I will introduce about the predator-prey model, which is known as the Locked-Volterra model. It describes the population between predator and prey. The population changed basically based on the interaction between each other, and also how the species population changed by themselves. Where X you see in the center of this slide is the equation of this model. The X represents the prey population, the Y represents the predator population. The parameter each year for alpha is the burst rate of the prey. So when alpha is big, the prey increase dramatically, and the beta is the pre-population decrease in response to interaction with predator. So if there has more interaction between a prey and predator, the predator will eat more prey, so the prey population will decrease a lot. And the gamma is the predator population increase in response to interaction with prey. So if the predator eats more prey, their population could increase based on this. And last one is the gamma, which is the death rate of the predator. So if the death rate is really high, the population of predator will decrease. The broader picture here is that we're going to use this predator-prey model to model the population change of the predator and prey in our system. And specifically, we're going to use this beta parameter to model the sensitiveness of predator of the prey, which will be explained by an SIR model that explained after this.
So we're using an SIR model to model the behavior of these squirrels. Traditionally, an SIR model is an epidemiological model that computes the theoretical number of people infected with a contagious disease and a closed population over time. So in our particular example, instead of looking at people, we're looking at squirrels or prey, and the infectious disease is actually the presence of humans. So this is a compartmental model, which means you have to be in one of the three populations: susceptible, infected, or recovered. A squirrel cannot have prey behavior and anti-prey behavior. Yeah, the susceptible population is a function of time, as we can see here, and values the basic reproduction number that contains things like our daily contacts parameters and the transmissibility. How much is a squirrel impacted by their interactions with a human? And then N is just the total population. So yeah, we're specifically looking at the differential equations. We want to see how these behaviors are going to change over time. So that's a function of each interaction between the susceptible and infected population over the total population. And it's impacted by the contacts and transmissibility. And then the recovery factor is exposure to foxes. So yeah.
Awesome. And here are some simplifying assumptions we're making. So we're assuming that the prey is just squirrels and the predators are just foxes. So we're not going to think about eagles or dogs or anything like that. The contacts that we're looking at are the interaction between squirrels and humans, foxes, and other squirrels. And we're assuming that that is a normal distribution. So with an average of 10, I think, for each of those. And so the normal distribution allows a little bit of wiggle room, like maybe one squirrel interacts with 6 humans that day, but then 12 humans the next day. The time frame is 1 calendar year, and we're assuming 104 days of summer vacation. Shout out Phineas and Ferb. And then the desensitivity, as Regan was talking about, a squirrel can only exist in one of the SIR. We're calling it SDR for desensitized. So we're assuming that a squirrel is either sensitive, desensitized, or resensitized, and no in between there. Some data we're using to support our model are that there are an average of 6,354 students on a college campus, an average of 85 squirrels per acre of college campus. So we're proposing a 100 square acre campus that gives us 8,500 total squirrels. And then we're supposing that each squirrel interacts with 10 students and 10 other squirrels on average, again, given that normal distribution each day. And the recovery rate, we're calling resensitivity, is the parameter by which squirrels regain their prey behavior. So after students leave the system, a squirrel has a 10% chance of being resensitized after interacting with a fox.
Cool. So the results of our SDR model, we have squirrels interacting with people, and with each interaction, there's a 1% chance that they will shift to their anti-prey behavior. Squirrels can also interact with each other or like other prey, and we're making the assumption that squirrels take each other's advice more often than squirrels will take advice or interactions from a human. So each interaction with another squirrel has a 2% chance of changing the squirrel's behavior. And lastly, remember, we're going to keep the foxes as part of our model, keep the predators involved. Squirrels can continue to interact with their predators, which returns them to the susceptible population for as long as humans are present. And what we're saying is there's a 10% chance, as Nicole was talking about, that they're going to interact with the fox and return to prey behavior. As we can see on this graph, with the 104 days of summer vacation, people are leaving the model at day 261. With that, our squirrel behavior, you can see with the green curve, they're finally joining this recovery or resensitized population. And over the course of about 50 days, they're returning to their full prey behavior. This is because squirrels are no longer susceptible to humans. Something to note and keep in mind with this SIR model, we're looking specifically at behavior, and the predator-prey model is actually what's going to be looking at the populations over time.
Next, I will talk about the results from our predator-prey model. On the upper right, the first picture is a population of squirrel versus foxes without considering the change of their sensitiveness to predator. So you could see that both of them are oscillating. However, since there are 8,500 squirrels at first and only 10 fox at the beginning, the graph doesn't show it in scale. It's not intuitive. Then we show the percentage of change of the population based on their initial population, which is shown in the second graph. You can see that the population of squirrel changed periodically, and also the fox population changed periodically. Next, we take into consideration of the predator, of the sensitivity of the predator, which is get from the SIR model, and then we draw the population plot. On the third graph, you can see that the population of the squirrel changed dramatically based on the population of the fox. However, they didn't get to zero because when the population of squirrel decreased, the population of fox will also decrease, which could restore the population of the squirrel. However, after 261 days, which is when people left, since the sensitivity of the squirrel do not acquire really quick, the population of the squirrel will decrease dramatically. So our final conclusion is that after people left a space, after people entering a space, they could cause some damage to the whole population and cause the change of the population of the predator and prey. And after people left the system, the damage has already caused, and the population of the predator and the prey will decrease dramatically afterwards. So next, what can we do? First, we could model what happens when human left in a predator-prey model for a long time. Since the damage is done, how long would it take for the system to recover? And next, we could combine the model in both ways. We could use the predator-prey model to change the daily population in the SIR model, which could make the whole models more realistic.
Yeah, we could also test our model. So how many squirrels do we interact with each day? What is the behavior that we see in these interactions?
And then finally, we could apply this model to a different set of data of what would this model look like on a big campus as opposed to a small campus? And what about maybe different species of squirrels interacting? And these are our sources, so thank you for watching.